Hi, and welcome to my live coding tutorial on building your own AI assistant in Java. This is going to be a very practical hands-on talk. We're going to go through just a little bit of theory up front to make sure that we're all on the same page. So I don't assume that you've built an AI-powered application before or that you're super familiar with all the concepts. If you are, feel free to skip right to the actual coding stuff. I'll make sure that there are chapters in the YouTube video. But I really recommend that you go through the couple of minutes of theory just to make sure that we're all speaking the same language as we get to the actual coding part. So this here is my dog Nova. Nova is 12 years, almost 13 years right now, so she's an old lady. About a year ago or so, we had to take Nova in for a CT scan because there was something odd with her spine, we thought. And it all went well, but for some reason the radiologist decided that the best way of giving us the report of her procedure was to print it out on a letter-sized paper, just 10-point font, super dense medical jargon. He printed it out, put it on a table, took a picture with a cell phone, and texted us the image with no explanation. So there we're sitting trying to decipher this really heavy jargon to understand what's going on here. We don't really understand all that's being said there. So as a nerd, as an engineer, what I did was I went to ChatGPT. I instructed it that it should behave as a radiologist who's also capable of human interaction. It should read through the report and report back any pertinent information in an easy to digest format. Sure enough, I got a report with a couple of headings, a couple of bullet points just explaining what's going on. Turns out there wasn't anything major going on that we should be worried about. And sure enough, the radiologist did call us about 4 hours later and told us the same thing. But that kind of just showed me that there's a tremendous potential for AI to do good things if we're using it correctly. But likewise, if you've ever used ChatGPT or any other tools like it, you've probably run into a situation where it's struggling to answer something that's seemingly simple, and you're like, why is it doing this? There's a big problem when we're building an AI-powered application specifically for a business or for a hobby project, and that is that LLMs are generic in the way that they work, whereas the problems that we're trying to solve in our business or in our hobby projects are not generic. They are very specific to a certain context where we are. And in order for the AI to be useful to us, we need to somehow kind of give it more information about our context, give it the ability to somehow interact with our system. Now, I work for a company called Vaadin. We are an open source company that helps Java developers build great web applications. Specifically, a lot of our customers are building web applications that are more business applications. These are the enterprise applications that run the world behind the scenes. And what I've seen in these applications over the years is that there's just a tremendous amount of inefficient workflows happening there. Something where I think AI could really help us just streamline things, make people's lives much better when they're working with these systems day out and day in. So that got me thinking, what are the tools out there for us Java developers to build these applications? How can we leverage stuff that's already there without having to really dig deep into the actual models themselves? What are the APIs that we can use to build stuff? The application that we're going to build is a simulated customer support agent for an airline. So here on the right side, we see a live view of our database, and we can kind of see the reservations we have there. And on the left-hand side, we have a chat with our AI representative. Now, what we want to be able to do is ask the AI assistant for information about rules, for instance, cancellation policies. We also want to be able to fetch our booking details. We want to be able to modify them, cancel a booking, obviously if that's permitted by our terms of service, and not if it's not. So there's a lot of kind of real world interaction with the system here, all distilled down to a very simple application that's kind of easy to reason about and for us to use for learning. One way of looking at building an AI-powered application that I personally find really helpful is to look at it as a computer architecture diagram. The LLM, or the AI in this case, is similar to the CPU in this case. So like I mentioned earlier, it's a fairly generic tool that is powerful, but in and of itself, it's limited in what we can do in our specific context unless we help it out. So at a very minimum, we need a context window, which is similar to the random access memory of a computer. So that's the working memory that we have as we're discussing back and forth and giving it information that we want it to work with. Very quickly, we'll also get to a point where we want to store some information more permanently. So for that, we're going to take a look at using a vector store to store information and fetch kind of the most relevant information that we need as we're answering a question. We also want to usually run some tools or programs in addition to just talking to the LLM. So essentially giving the AI the possibility to run some stuff for us. And we sometimes want to hook up some other LLMs or other models to our LLM. So for instance, if you've ever used ChatGPT to generate an image, it's essentially one LLM generating a prompt for a diffusion model that then generates that image for us. So we have these models that are designed to do different tasks, and sometimes it's good to kind of have different tools do different tasks for us. This is going to be a very hands-on talk, like I said. It's an engineer talk. We're not going to go into the math of how AI models work. I'm not the best person to explain how that works. There are a lot of better videos on YouTube for that. What we are going to use are the APIs that we have available to us as Java developers to build on top of work that other people have done for us. And hopefully you're going to see that thanks to all the tools that are available, it's going to be very simple for us to put together AI-powered applications without having to know all the kind of internal workings of an AI, which is super powerful. We're going to be working with two main tools here, in addition to Spring Boot, which is the base of our application. One is LangChain4j, which is initially was a port of the LangChain project for Python for Java. Since then, it's kind of taken on its own life, where it's kind of pulled in a lot of ideas from different libraries, some own original ideas, and become a very kind of popular and rapidly developing library in the Java ecosystem for doing AI stuff. The other tool that we're going to use is a open source full stack framework called Hilla from Vaadin. This is going to allow us to build a front end UI for our application so that we can live see kind of and interact with the application as we're building it. We're going to take a look at how that works in just a bit. I'm going to structure the talk along this axis of agent autonomy. So at the very kind of lowest end of autonomy that we give to an AI when we're building an application would be a chatbot. So this would be your original ChatGPT, where you can ask it questions and it will answer based on what it knows, based on its training, but nothing else. So it doesn't have access to the internet, it doesn't have access to your personal data or anything else. So it's sort of limited in what's able to do. It can be useful in some cases, but when we're building a custom application for a business or for a hobby, we very often at least want to go to a retrieval-augmented generation or a RAG state of kind of agent autonomy. This means that we provide the AI with some relevant context for answering the question as we're asking it, which makes it a whole lot better at answering questions that are specific to our context. In this talk, we're going to go all the way to the Copilot stage, which is where we give the AI the ability to not only have access to some custom information about our context, but also the ability to use some tools, in our case, fetching booking details for the airline customer, changing bookings, canceling bookings, and so on. If we were to go all the way to the other end of the spectrum to a fully autonomous AI agent, that would essentially be us just asking the AI to do the entire task for us, beginning to end without any human interaction. Well, I think there are going to be systems like this in many contexts in the next few years. I think within the business application context, we're going to be more comfortable being still in the pilot seat ourselves and just having the AI being the co-pilot. So we're not giving just SQL access to our database to the AI and say, go at it and see what happens, because we want to have a little bit more kind of structure and control in between. All right, so let's take a look at building a chatbot. What does that actually mean? In our previous analogy with the computer architecture diagram, that means that we are working with the LLM or CPU together with a working memory, which is the context window. So a context window is essentially the memory that we have available to us as we're working with the LLM. And this is where we need to kind of fit everything that's relevant for what we're working with. So this would include the system prompt. In our previous example, that was me instructing ChatGPT to act as a radiologist that's capable of human interaction. We need the entire history of our chat, the kind of messages back and forth, because without it, the LLM does not know what we're talking about. It doesn't maintain its state internally. That's something that we need to provide. Of course, we need the prompt, whatever we're asking at the moment. Very likely, when we're doing the RAG part of this, we'll also want to include some relevant information for answering that question. And what's important is also making sure that we have enough room for the answer to be provided as well. So if we had a very small context window with a kind of a smaller local model, say 4,000 tokens, if we filled that with 4,000 tokens of input, we wouldn't have any room for kind of getting output. Now, context windows have grown a lot in the last year, going from this 4,000 tokens that we had just not long ago to more than 1 million tokens now. So conceivably, we could start adding a lot of information in this context to the LLM. Now, the problem there is that we're getting charged by the amount of tokens that we use. So we have an incentive to not use more tokens that we absolutely need. And for the most part, the LLM is going to be more efficient and kind of good at answering the question if we only provide relevant information, as opposed to just add all the information in the world to that prompt. So it's good to keep in mind there. All right, so let's take a look at retrieval-augmented generation. So this is where we add a persistent storage component to our architecture diagram. So this is a way for us to pull in relevant information for answering a question. So an LLM language model knows two things. So first of all, whatever they've been trained on. If we're talking about the big models like OpenAI's GPT-4 or 4o or o1 or any of the new models, they are all trained essentially on the entire internet up until some certain point in time. The other thing that they know is whatever we pass in to that model as part of that context. So if we wanted to teach an AI new things, we have a few options. We could train our own model. It's great if we have several months and hundreds of millions of dollars to do it. So we're not going to do that here. We could fine-tune a model. So essentially taking an existing model and teaching it some new tricks on top of what it already knows. So we give it some more kind of examples of how we want it to behave in certain situations, more information about our specific business context, and so on. This is really good for more static stuff within our business context, but absolutely the cheapest and easiest way of doing this is adding the relevant stuff into the context window as we're asking the LLM to provide us an answer. This is essentially us giving the LLM an open textbook exam where we ask it a question and pass it the textbook open on the right page, just asking it to read through this page and then answer the question. And it's really, really good at answering that question, provided that we give the right information for it. So how does that work? If we have a ton of information, how do we pull the right piece of information to pass in? So how do we open the right page in the book for the LLM to answer? So we're going to work with a terms of service document. In this example, it's very small. So this is more indicative of how you would do this for any number of documents. But what we want to do is, as we're reading in documents, we want to split those documents into segments of reasonable size. In this case, we're using the headings in our document to segment the document into reasonable pieces. What we're going to do then is we're going to take that text, we're going to run it through an embedding model, which will give us a vector representation of the semantic meaning of that text. Now that's a little weird the first time you run into it, like what is a vector version of the semantic meaning of a text? So let's take an example just to kind of clarify what we're doing here. So if you've ever used a color picker, you probably know that you can pick any color essentially in the color spectrum and you get a vector value, a red, green, blue vector with 3 values that describes that colors. So if you pick 2 colors that are very close to each other, you intuitively know that the vector values for those colors are going to be very similar. Whereas if you pick 2 colors that are very far apart, those vector values are going to be far apart. So we're essentially doing the same here with text instead of colors. So we're capturing the semantic meaning of a text into a vector that's not 3 values, but it's 1,500 values. It might be 3,000 values in that vector where each number just represents the similarity in some dimension that we don't need to know what it is. We just need to know that texts that have a similar meaning will have a very similar vector value. And that's why we're splitting up the text in these segments. So if we didn't split up a document into segments, we would essentially be asking the color picker for, give me the color of this entire image. Whereas if we can be more specific and ask, like, what's the color of my watch armband, that's going to give us a much more relevant answer when we're asking that question. All right, so we've taken the text, we've gotten embedding values by calling an API that gives us this vector value. We're going to take those and put them into a vector store, which is a database that's good at doing vector math. And what we can do then is when a user comes in and asks us a question, in this case, what's the cancellation policy? We run that text through the same embedding model to get a vector that represents the meaning of that question. In this case, we can assume this vector somehow has to do with cancellation. So we go into our vector database, we ask like, hey, what is the most similar document you have that has something to do with cancellation? And that should hopefully give us the cancellation section of our terms of service. And then we can take our question, what's the cancellation policy, and instruct the LLM to answer using the provided documents, in this case, our cancellation policy. And that's going to allow it to give a really good answer for us. All right, finally, let's take a look at how we can go to that next step, the Copilot stage of agent autonomy. So this is essentially us adding the ability to run some tools into the mixture. So essentially how this works, if we look at the interaction between our application and the LLM, is that when we make a request to the LLM, we add some metadata to that request saying like, hey, there are functions that you can call if needed. So in this case, our user is saying like, hey, my name is John Doe, my booking number is so-and-so, can you pull up my booking? And then hidden to the user, we're also sending to the LLM information like, hey, by the way, there is this method called get booking details that takes in a booking number and a name. So the LLM looks at that, it's like, okay, I don't know anything about this booking number, but I see there's a function I could call that gives me that information. So it will extract the relevant information out of the text, and it's going to ask our application then to run that function with those parameters that it gives us. So we run that on our end, and we give back the information to the LLM. And at this point, it has the question and it has the answer from running that function. And that's all that it needs to provide the relevant information to our user. So by having this one back and forth where the LLM can run code, allows us to give it a whole lot more power than it would without it. All right, and then the final thing that we're going to look at before we get to the actual coding part is how do you build a UI with Hilla. So Hilla is a full stack React framework for Spring Boot by Vaadin. It comes with this big library of UI components that are the building blocks that we need when we're building apps. Anything from small text fields and buttons all the way up to like full-blown data grids and charts and so on. These are all very customizable, so we can configure the look and feel of these components to really match what we're going for. They're all exposed as React components. So if you want to have, for instance, a grid like here, we create a grid component, we define the paths out of the objects that we want to have shown, and then we just pass the grid in an array of objects and it will display them. Hilla is a full stack framework, meaning that you have both the front end and the back end code in the same project. It uses similar file system based routing as Next.js, for instance, where the view name is corresponding to the URL that it gets routed to. So if you have an index.tsx component, it will be mapped to the index. If you have a about.tsx, it will be mapped to about, and so on. What's really special about Hilla is how we actually interact with the backend. Since this is a full stack application, we're not creating generic REST endpoint services, for instance, but we're calling service classes created as Spring Beans, and we're adding this browser callable annotation on them, which will make them callable from our React front-end code. In this case, we're also adding a anonymous allowed annotation because we're not setting up Spring Security in this particular demo, but if you were using Spring Security, you could configure access control here as well. What's cool then is in our React code, we can call that same method signature with the same type information in this case, we're awaiting the contact service find all, and we can expect to get a array of contact objects. All of the types have been automatically generated for us, as well as the actual TypeScript code for calling that service. So in the application code, it looks like we're just calling a TypeScript method that calls the Java method under the hood. So it's a seamless kind of way of calling the backend with full type information, which means that if somebody changes our backend code for whatever reason, we would get a compile time error in the React view instead of noticing that sometime later down the road. All right, that's enough talk. I think we are ready to get going with the actual coding. So let's hop on over to IntelliJ and see what we have. Okay, so here we have the same application that we saw in the slide. So here on the left-hand side, we have the support chat, and then on the right-hand side, we have a live view of our database. So right now, if we say something like hi, it's just going to say, hello, my brain is not yet hooked up, because we haven't actually done anything yet. So that's our task for today, is implement this assistant. I'm going to share the code for this demo in the show notes and later on in the slides as well. So just pay attention to the kind of concepts here, and you can find the code later on if you want to play around with it. So our project, if we take a look real quick at what we're starting from, is a Spring Boot project where I've added the Vaadin Spring Boot starter dependency, so we can add those React views to the application. And I've added the LangChain for J dependency, specifically the Spring Boot starter version that takes care of a lot of the kind of auto configuration for us. In addition, I've added the OpenAI Spring Boot starter, which means that we're going to use the OpenAI model. If we wanted to use a different model like Gemini or Ollama or something else, we could change the artifact here and use that instead. All right, so then if we take a look at our source code, source folder here, first of all, in the resources, application properties, added a couple of properties here for LangChain for J. Specifically, I've added my OpenAI key from an environment variable. We're going to use the streaming model, meaning that we want the answer to be streamed to us as it's getting generated by the AI. We're defining which model we want to use, GPT-4o in this case. And likewise, we're going to use the OpenAI embedding model to get those vector values based on a string. Finally, I put the temperature to 0 here, so we don't get as much randomness in the answers as we would otherwise. And also I've added some logging here so we can look at the back and forth between the AI and our application. In the resources folder, I also have our terms of service document, which is the same one that we just looked at. So that's the one that we're going to be using throughout the demo here. In the Java folder, we have a Spring Boot application. We have a service that provides all the kind of CRUD operations we need for finding all the bookings and changing them and so on. We're just exposing the booking details here, which are the same that we're showing here in our grid. We're not going to go too deep into how that's implemented because it's not really relevant to us using it. In the client package here, we have two services that we're going to use from the client. So one is a booking service, again, has this browser callable, so we can call it from the browser. And it uses the flight service to just return all the bookings that we display in the grid. And then what we're going to be working with here is the assistant service, which is going to be how we interact with the assistant. So it's a browser callable again. It has one method here that returns a flux of strings. A flux is something that we can subscribe to and get notified whenever new values are produced. So in this case, as new tokens are generated by the LLM, we can append them to the UI. Right now, it's just displaying a static text here, the one that we saw in the UI just a moment ago. And this is where we're gonna go in and implement stuff. Then on the front end side of things, we can go into our source main front end views folder here, and we can find our React view, which is what we see here in the browser. So a React component, if you're not familiar with it from before, has two main parts. It has a state, which is the state of the component, essentially the model. we're tracking a few things here. So we have an ID that's unique per chat so that your chat and my chat histories don't get mixed up. So it's essentially a key in a map on the server later on. Then we're tracking a Boolean for whether or not we have an ongoing request going so that we can kind of disable the button here while we're generating stuff so we're not sending multiple requests at one time. We have a array of booking details, which is what we're binding to the grid here. And then we have an array of message items, which is what we're showing here on the side. All right, so then the other part of a React component is the template that we bind this state to. So we have a split layout, which is a one component wrapping the whole thing, which gives us the ability to resize the UI here. Then we have the grid here, which is bound to our array of bookings and just defines switch paths of that object that we want to display here. On the other side, we're displaying a message list that's displaying all the messages that we have. And we have an input that calls this send message whenever we hit submit. Send message does a couple of things. So first of all, we set our working Boolean to true. And because that Boolean is bound here to the disabled attribute, it will automatically disable the input whenever it is true. All right, so we set the working to true, then we add our own message so that we have immediate feedback in the UI that we sent that message. Then we call the assistant service. So this is the Java service that we just looked at. So assistant service.chat. We're calling assistant service.chat. Then we subscribe to the next token. When the first token gets generated, we add the AI bot's message to the message list. And then as more tokens get generated, we just keep appending them to that last message. All right, so that's all for the UI. We're now going to focus in on actually implementing that AI assistant. So let's start by going into the service package here, and I'm going to create a new Java class here. I'm going to call this my assistant like this, and it should actually be an interface like this. So if you've ever used Spring Data, you know that you can create a interface of a JPA repository, and Spring Data will provide you with that implementation. So very similarly to that, LangChain4j can provide us with an implementation of an interface that we define on how we want to interact with an LLM. So in this case, we have an assistant interface, and here we're going to define the method that we want to use to call the AI. So we're going to have one single method that returns a token stream, which is a LangChain4j specific data type that represents a stream of tokens. We're going to call this chat, and it's going to have the same exact signature as our chat in the service. So we're going to have a string for the chat ID, and then we're going to have a string for the user message like this. We're going to add some annotations here just to tell LangChain4j what we're doing here. So this is going to be the memory ID. So this, again, the key that identifies my chat from your chat. And this is going to be the user message that we have. So that's all we need to do to define how we want to talk to the AI. The actual setting up of all of this is handled by LangChain because we have that OpenAI dependency. It's going to use OpenAI, and because we have that OpenAI key in our properties, it's going to set up all of that for us. So let's go into our assistant service and inject a instance of this assistant into our class. So I'm going to create a private final assistant like this, and then we're going to create a constructor where we get that injected for us. So what we can then do here is call that assistant and pass the stream of tokens to the client. Now I'm using a version of LangChain4j that does not yet support returning a more standard flux of strings. We're using this token stream, so we need to do a little bit of work here to convert between LangChain4j stream to a more standard flux. There's a update coming in the next couple of weeks from me filming this that's going to take care of that, where you can just return the flux. So don't worry about it too much. We're going to code through this together, and if you watch this in a few weeks, you don't have to do any of this. So I'm going to manually create a flux that we then pass through these tokens through. So I'm going to use a syncs.many of type string, and I'm going to type this out and then explain what's going on. So I'm going to call this my sync, and this will be a syncs.many.unicast.back pressure buffer, meaning that we are going to have many tokens flowing through it. They're all going to the one person who initiated the chat. And if for whatever reason we're generating more tokens than the client is able to handle, we should buffer those so we don't want to lose any kind of parts of the word in the middle of a sentence, because that would be super confusing. And then we can take the sync and return it as a flux to get that to the client. So here in between, we need to kind of pass those tokens from one stream to another. And that looks something like this. So we take the assistant, we call the chat method, we pass in the chat ID, we pass in the user message. Then we say that on next, we're going to pass that token to the syncs try emit next. Whenever it completes, we have a slightly mismatch in the APIs here. So we're going to call sync.try emit complete. And then whenever there's an error, we're going to call the sync and try to emit an error. And then finally, we need to call start to actually initiate that call. So a little bit of plumbing code here, not too bad. And with, I think, LangChain4j 0.35, this is something that you no longer need to do. You can just add a dependency for, I think, Project Reactor, LangChain, something like that. Check their GitHub to see how that works. But in that case, you can just skip all of this. All right, so very good. I'm going to go ahead and build the project. So I'm going to call build here. And since I have Spring Boot DevTools, that's going to cause my browser to automatically reload when that's done. And hopefully, if we now interact with this, we could ask it something. So I'm going to use the dictation on my Mac to save us from having to type stuff, and hopefully it works. Hi, who are you? All right, so now we're no longer getting that pre-canned response. Instead, it's saying like, hey, I'm OpenAI's language model and so on. So this is technically true, but also it highlights this kind of dissonance that we have between the LLM being very generic and our app code being context specific. So in this case, we would like our assistant to actually identify itself as a customer service representative for our airline. So let's go ahead and do that. So I've prepared a prompt here, and we're going to go into the assistant here, and we're going to add a system message annotation here where we define how we want it to interact. So we're saying to our assistant that it's a customer chat support agent for Funair. It should be friendly, helpful, and joyous. And I've instructed it that it's interacting with customers through an online chat system because it was kept kind of putting me on hold. So it really kind of took to heart this being a customer support agent a little bit too eagerly. Then before providing information about a booking, it needs to make sure that it has a booking number, first name, and last name. And before changing a booking, it should make sure that it's permitted by the terms, which we're going to pass it a little bit later. And if there's a charge, it needs to get consent before proceeding. And then we're lastly here passing in today's date, just so it knows what day it is today, because again, it does not know anything about, it doesn't maintain a state of its own. So that way it can see, is our booking kind of far enough into the future that the cancellation policy allows people to do changes. So again, I'm going to build the application here, and hopefully when it reloads, we can get a assistant that is aware of who it is. Hi, who are you? All right, so there we have it. So now it's identifying itself as our Funair customer support agent. There's still a slight problem here with the context window in that we are not tracking the message history in any way. So just to illustrate how that works. Hi, my name is Marcus. So here we've given it a piece of information. And if we now ask it to somehow kind of pull up that information again, it's going to fail. I seem to have forgotten my name. Can you please tell me what it is? So here, like logically, it should be able to know that my name is Marcus because we just told it my name is Marcus. But because it does not maintain that chat history, it's unable to do it. So it's being helpful in the way that it's like offering to try to figure it out by looking up a booking number and so on. But that's not really what we want to do here. So let's go back into our service package here and create a new configuration class. I'm going to call this my LangChain4j config. Like this. We're going to add a configuration annotation here, and we're going to start defining some beans. And when LangChain4j finds these beans on the class path, that's going to tell it to start using them. So in this case, we're going to have a bean that is a chat memory provider. We call this our chat memory provider, and I'm going to inject a tokenizer, which is something that LangChain uses to calculate how many tokens a given string is. So we're going to return a lambda that takes in a chat ID as its key, and then it returns a token window chat memory. So here we just essentially say that we want to keep a window of 1,000 tokens at most in our memory. So whenever we start having more than 1,000 tokens worth of messages, it's going to start dropping the older messages out of the history. So again, let's go ahead and build this and see what happens. So again, I'm going to try the same thing as we did before, and hopefully this time it works. Hi, my name is Marcus. All right. I seem to have forgotten my name. Do you know what it is? And there we have it. So now it's able to actually refer back to our previous discussion to kind of gather that information the way that we would expect it to work. Now, this is already kind of helpful, but we're still at that chatbot stage of agent autonomy. So what we want to do next is go to that RAG stage of agent autonomy and make it aware of our specific business context, in our case, our terms of service. So let's go into our configuration file here and start defining some more beans. So for this to work, we essentially need to walk through all of those steps that we did in the slides of splitting up a document into sections, running them through this embedding model, and then kind of putting them into a vector database and pulling them up based on kind of querying that vector database. All right, so there are a couple of things we need to do here. First of all, I need to define a vector database. So I'm going to do an embedding store that stores text segments in our case. And this will be our embedding store. And we're going to return a new in-memory embedding store. So the in-memory embedding store is, as the name suggests, just runs in our JVM. It's not super powerful, but it's super easy and kind of handy for demos like this. What's beautiful about LangChain4j is that this is an interface. So by just changing this to whatever actual database you are running, you can kind of start with something simple in memory and then kind of update that to an actual database later on without having to change the rest of your code. The embedding model we already configured here in our application property. So by giving the API key to LangChain4j, it's going to use the OpenAI embedding model. Again, the embedding model is what takes a string and turns it into a vector. Okay, so we have the database. We have a way of turning texts into vectors. So the next thing that we need to do is read in that file, segment it, run those segments through the embedding model, and store them into our vector database. Now, this is something that you wouldn't do in the actual application in real life. Here we're building a self-contained demo, so I'm going to do it here. But in reality, you don't want to be rerunning all of this work on every time you start the application. So more likely you would have this piece of code on a build server somewhere that gets notified whenever a piece of documentation changes and just updates the vectors for that specific document. But here, let's keep everything simple in one place. So we're going to create a application runner that gets run whenever the application starts. We're going to call this our ingest docs function. This needs to return arguments like this, and here we can run our code. So we need to add a couple of things, or inject a couple of things here. So we're going to have a embedding model, and we're going to use the embedding model for LangChain for J. We're going to call this our embedding model. Then we're going to have a embedding store, the one that we configured up top. We're going to call have text segments again there. Then we need the tokenizer that we used earlier. And then finally, we need a handle to that text file that we had. So I'm just going to, again, we just have one file here. So this is kind of straightforward enough. We're going to use a value annotation here to get from the class path the terms of service.txt resource. We're going to call this our terms of service like this, and we're going to reformat. Okay, so what we need to do is we need to take this resource and load it into a LangChain for J document. So let's call this our doc, and we're going to use the file system document loader, load document. It takes in a path. So we're going to take our terms of service. We're going to get the file and turn that into a path, and that gives us the document. Then we need a ingester, which is a something that takes in any number of documents and runs them through this pipeline of splitting them into sections, running each section through an embedding model, saving them to a database. Here we're using the embedding store ingester from LangChain. We're going to do everything by hand here just to kind of show you all the steps. There are kind of pre-configured versions of the ingesters that make things a lot easier. So for instance, there's a convenience one that just takes a path to a folder, and just based on file names, it will automatically kind of read in anything that you pass in. But here, as we're trying to learn things, we're going to be very explicit in how we do things. So we're going to start by taking in the document, and we're going to split it. So we're going to define how we want to split it. We're going to use the document splitters.recursive. And we're going to say that we want segments of 50 tokens with no overlap. And we're going to use that tokenizer to count how many tokens a given string is. So the recursive splitter here means that we try to fit an entire paragraph into that segment. If it's too big, then it's going to split it based on sentences recursively into smaller and smaller pieces until it's able to fit them into 50 tokens here. All right, so we have a segment. Then we're going to run it through our embedding model like this to get the vector. And then when we have the vector, we're going to save the text and the vector into our embedding store like this. All right, so then we have the pipeline for handling the document. And finally, we need to take the ingester and ask it to ingest our document. And again, this would run on a separate build server more likely than in your actual application in the real world. So if we go back to how our application actually consumes this information, we need to define a content retriever. So again, a bean here for a content retriever like this. We need the embedding model here again. So embedding model, and then we need the embedding store like that. And what we are going to return here is a embedding store content retriever. Again, we're going to be explicit and do this by hand just so we see all the steps. So essentially, when a user asks a question, we want to run that through the embedding model to get a vector, and then we want to use that vector to search the embedding store. So we take the embedding model here, so it turns it into a vector, and then we take the embedding store so we can search for it. We are going to say that we want to have a maximum of 2 results, and those results should have at least a score of 0.6. So how relevant are they? So we don't want to have stuff that's completely irrelevant added to that context window because it's going to confuse the LLM potentially. All right, so let's go ahead and build. If things went well, we should be able to ask this some more useful questions. So let's see here. Can you explain the cancellation policy to me, please? All right, so we're getting some stuff here. Let's verify that we are getting the right information. So we can see that you can cancel up to 48 hours before. The fees are $75, $50, and $25. And let's go into our terms of service here. So sure enough, 48 hours before flight, 75 for economy, 50, 25. So that is correct. All right, so the next thing we want to do then is give the AI the ability to run some tools for us. So in this case, fetch our bookings, make changes to the bookings, cancel the bookings, of course, if they're allowed by the terms of service here. So for that, let's go ahead and create a new class here. I'm going to call this my booking tools. And this is going to be a Spring component. And we're going to inject that flight service that we use for actually managing flight bookings. So we're going to create a private final flight service like this. We're going to create a constructor to inject it. And here we're going to create three methods. So one for getting a booking, one for changing a booking, and one for canceling a booking. So let's create a public method that returns booking details. And it's called get booking details. Here we're going to ask it to get in three parameters: booking number, first name, and last name. So we're going to take in a string booking number, string first name, string last name, like that. And we're just going to delegate this to our flight service like this. Here I'm using GitHub Copilot just to kind of save us from typing a little bit. So the second thing we're going to have is for changing a booking. Here Copilot kind of guessed the API wrong. So let's go in here and take a look at what the actual signature looks like. And we're just going to have the same signature here. I could technically just have it right away, just call the actual flight service, but I want to kind of have this one tool class here in between, so it's more explicit what I'm giving it access to. And then finally, we're going to have one for canceling the booking. So in order to make these now available to the LLM, we're going to add a tool annotation here. We could give a description here to make it more apparent to the LLM what this tool is for, but since we've been very kind of explicit in naming the methods and the parameters, it should work just as is. So we're going to make all of these three tools available to it. And hopefully by the time we get here, we are able to do some meaningful things. So the way I set up the text data here is that the people who are at the beginning of the data set are too close to their travel to make any changes or cancellations, whereas people who are towards the end here should be able to do it. So let's have a simulated discussion here, starting with being John Doe, and see if we're able to do what we want. Hi, my name is John Doe. Can you pull up my booking details? All right, so here I forgot to give my booking number, but it's asking me for that. So let's go ahead and provide it. It is 101. All right, so sure enough, here we get our booking details. And again, the user wouldn't be seeing the database view directly, but here we can see that it does match what we have in the database. Here it's interesting to kind of go in and see what's actually going on beyond, kind of behind the scenes, kind of how are we communicating with that LLM. So if we look at what the actual post message to the REST API looks like, you can see that we have a history of the messages here. So we have the system message that we provided, then we have the back and forth that's been happening here between us. And what's interesting here is that we can see the assistant here asks to do a tool call to the get booking details with these booking number, first name, last name that it extracted out of the message history. And you can see that we've defined here as metadata which tools are available to the LLM, so we can see all the different functions that we have available here, what are the required parameters, and so on. So we have the three functions defined here. So that's how that works. All right, so good enough. We have our booking here. Let's see if we're able to cancel it. Hi, can you please cancel my booking? So let's see what happens here. So it's making me aware that there's a cancellation fee. Okay, let's see what's happening. Sure, please go ahead. All right, so it took it a little while here. Ideally, it would have noticed already earlier that no, we're too close to it, but better late than never, I guess. So it's telling John here that no, sorry, can't do. We are too close to the flight for you to make any changes. All right, so let's take a look at another example here. So let's pretend to be Robert Taylor and make a change to our flight here. Hi, my name is Robert Taylor. My booking number is 105. Can you please change my flight to Helsinki instead of Frankfurt on the same day? So let's see what happens. All right. For some reason, it's asking me for my last name. I already provided it. Check the last message. Let's see if that works. Okay, so here we're running into this same weird problem that I've had with GPT-4o for some reason, where it's putting me on hold. But let's go ahead and say okay here and just let it continue on here. And sure enough, here it's pulling up my details. Here it's saying that there will be a $30 change fee. So let's go ahead and say yes. And hopefully this time around, it will actually go ahead and update that. And here you can see that it was able to deduce the airport code based on the kind of just plain Helsinki description. So we didn't have to provide all the information. It was able to deduce some of this by itself. All right, let's see if we can also cancel the booking. Actually, I changed my mind. Can you please cancel the booking? Let's see if that works. All right. It is successfully canceled. So there we have it. We did not spend a whole lot of time, but we were able to build a fairly meaningful application where we're able to interact with our actual data in our system. We're able to perform operations. We're able to use our own context, in this case, our terms of service, to kind of ground this discussion in some reality that's relevant for us. You can find this project on my GitHub. You can use the QR code here, and I'll put it in the show notes below as well. And here in this project, you can find the same project implemented with LangChain4j that we did here. There's also a Spring AI branch in the document for how to build the same application with Spring AI, if that's something you'd prefer. And there's also a Microsoft Semantic Kernel version branch as well. So if that's more your jam, you can kind of see how all these three libraries compare to each other. All right, so there you have it. Thank you so much for watching. If you find this video helpful, please go ahead and subscribe and like, and I'll see you in the next one. Thanks, bye.